Imagine you are cruising at 37,000 feet, the autopilot engaged, the cabin quiet. Then, without warning, your airspeed indicator plummets to zero. The autopilot disconnects. The stall warning blares. You have just been betrayed by a simple metal tube. The Pitot tube, a device so small and seemingly reliable that pilots rarely think about it. Invented in 1732 by Henri Pitot to measure water flow, this tube has a darker role in aviation. When blocked by ice, insects or debris, it can lie to pilots. The airspeed indicator may read zero, or worse, overread, convincing the crew they are flying faster than they are. The FAA's handbook warns, a blocked Pitot tube can cause the airspeed indicator to act as an altimeter. This means as the plane climbs, the airspeed appears to increase, a deadly illusion. This illusion played a role in 3 catastrophic flights, where crews trusted their instruments until it was too late. So how does a simple metal tube measure the speed of an aircraft? The answer lies in a principle discovered in 1732 by the French scientist Henri Pitot. He found that a tube facing into a moving fluid captures the full pressure of the flow, a force called dynamic pressure. That dynamic pressure is compared to the static pressure of the surrounding air, measured through small ports on the fuselage. The difference between these two pressures drives the airspeed indicator, but the same system also feeds the altimeter and vertical speed indicator. In normal operation, the system is elegantly simple. No moving parts, just air pressure pushing against flexible diaphragms inside the instruments. But that simplicity comes with a vulnerability. If anything blocks the Pitot tube or the static ports, the readings become dangerously wrong. The FAA Pilot's Handbook of Aeronautical Knowledge warns, a blocked Pitot tube can cause the airspeed indicator to act as an altimeter. When the Pitot tube is blocked but the static port is open, the indicated airspeed reads zero at low altitude and increases with altitude, a false climb indication that has fooled many crews. So how exactly does a Pitot tube fail? The most common culprit is ice. At high altitude, supercooled water droplets can freeze on the probe's opening, slowly choking off the ram air pressure that the airspeed indicator depends on. But ice isn't the only problem. The FAA's handbook warns that a blocked Pitot tube can cause the airspeed indicator to act as an altimeter. If the drain hole is also blocked, pressure is trapped, and the reading becomes stuck or erratic. Then there are the unexpected blockages. In 1996, Bergen Flight 301 likely took off with a wasp nest inside its Pitot tube. The nest blocked airflow, causing the airspeed to read falsely high. The pilots, confused, pushed the nose down and lost control. Ground handling also takes its toll. Maintenance crews sometimes forget to remove the protective covers over Pitot tubes, or a simple bump from a service vehicle can dent the delicate opening. Any deformation changes the pressure reading, silently corrupting the data. But here's the catch. The most dangerous icing doesn't happen during descent into visible clouds. It happens at cruising altitude, where the air is cold and thin, and where pilots trust their heaters to keep the probes clear. That trust, it turns out, can be misplaced. So why would a heated probe still ice over? NASA research has documented a phenomenon called run-back icing. When the heater is on, ice can melt and then refreeze just behind the heated zone, forming a ridge that disturbs the airflow into the tube. The FAA's handbook notes that a blocked Pitot tube can cause the airspeed indicator to act as an altimeter, but at high altitude, with ice partially blocking the probe, the readings become erratic, jumping, dropping, or freezing entirely. The crew loses their primary reference. This is the twist. The very system designed to prevent icing, the heater, can sometimes make the problem worse. And because the failure occurs at cruise, in clear air, the crew has no visual cue of ice on the probe. They are flying blind, trusting instruments that are already lying. So why did 3 crashes in 13 years share one culprit? Each began with a Pitot tube failure, but the disaster came not from the blockage itself, but from the confusion it sowed in the cockpit. On October 2, 1996, Aero Peru, Flight 603 climbed out of Lima into the night. But maintenance workers had left adhesive tape over the static ports. The altimeter froze, the airspeed indicator read wildly wrong, and the crew, flying blind over the Pacific, descended into the sea. That same year, Bergen Flight 301 took off from the Dominican Republic. A wasp nest inside the Pitot tube caused the airspeed to read falsely low. The captain, trusting the instruments, pushed the nose down to gain speed, but the plane was already going fast. It tore apart over the Atlantic. This illustrates how a simple blockage can create a deadly chain of events. The most infamous case came 13 years later. Air France Flight 477, en route from Rio to Paris, encountered ice crystals at 35,000 feet. The Pitot tubes iced over and the autopilot disconnected. The crew, faced with contradictory airspeed readings, pulled back instead of pushing forward, and the Airbus stalled into the Atlantic. The mechanism: ice crystals blocked the Pitot tubes, causing erratic airspeed data. In each case, the Pitot tube failure was survivable, but the crew's confusion turned a sensor glitch into a catastrophe. The lesson is brutal. A tiny tube can bring down a plane, not by braking, but by lying. So how do pilots survive when their primary airspeed data vanishes? The first line of defense is redundancy. Modern airliners carry 3 or more Pitot probes, each with its own heater, ensuring that if one fails, the others still provide reliable data. But hardware alone isn't enough. Pilots are trained to recognize unreliable airspeed from other cues: engine power, pitch attitude, and GPS ground speed. The FAA mandates that every pilot master the unreliable airspeed memory item, a checklist that can save lives. This training proved critical in 2018 when Southwest Flight 1380 suffered an engine failure that also damaged its Pitot tube. The crew, relying on backup instruments and their training, managed to land safely, a testament to the human factor in aviation safety. But heaters themselves can fail. A broken wire and a short circuit, or a burned out element can leave a probe defenseless. And because the heater is buried inside the tube, there's no visible warning until ice forms and the airspeed starts to drop. So the Pitot tube isn't the only vulnerable point. The static ports, which measure outside air pressure, are equally critical. If they ice over or get blocked, the altimeter and vertical speed indicator also fail, compounding the confusion. There's another hidden failure. Pitot tubes have a small drain hole to let moisture escape. If that hole gets blocked by dirt or ice, pressure gets trapped inside. The airspeed indicator then reads stuck or responds only to altitude changes, not speed. What happens when multiple probes fail at once? In some incidents, ice or debris block 2 or 3 Pitot tubes simultaneously. The flight computers then detect disagreement and revert to a degraded mode, but the crew must still diagnose which data to trust. So the key to survival is crew coordination. When airspeed goes haywire, the pilot flying must focus on pitch and power, while the pilot monitoring cross-checks with GPS ground speed and other instruments. Clear communication is vital. That's why airlines now train for unreliable airspeed in simulators. Pilots practice recognizing the signs: unusual control forces, unexpected stall warnings, and data mismatches. This training has turned potential disasters into manageable events. After Air France 447, the industry overhauled Pitot tube designs and replaced older models with more robust ones that resist icing better. But hardware alone isn't enough. The human factor remains the final safeguard against a tube's lie. But there's another icing mechanism that's even more insidious. Ice crystals can be ingested into the Pitot tube from the outside, bypassing the heater entirely. These crystals melt inside the tube and refreeze further down, blocking the airflow from within. When the Pitot tube blocks, the stall warning system can trigger falsely. The aircraft's computers detect a drop in airspeed and assume the wing's about to stall. This happened on Air France 447, where the stall warning blared, even though the plane was not aerodynamically stalled. So how do crews know if the Pitot heater has failed? Some aircraft have a heater failure indicator light, but it only shows a complete electrical failure. A partial failure, where the heater works but not enough, goes undetected until ice forms. So the humble Pitot tube, a simple metal tube facing into the wind, is both a marvel and a menace. It reminds us that in aviation, even the smallest component demands respect, and that the difference between safe flight and disaster often comes down to vigilance.